So thanks for coming. I know it's the second day and it's late and we're the last thing that stands between you and beer or dinner or whatever. So hopefully we'll be able to make this interesting, right? Cool. So anybody know what this building is? Burj Khalifa. The Burj is the world's tallest building today in Dubai. It stands at around 2,700 feet. Right? The spire is visible from supposedly 60 miles away. It's got both the world's highest nightclub and the world's highest mosque. Right? So this building is so tall, the top is 20 degrees cooler than the bottom. Right? And so this is a pretty, I don't know, effing amazing feat of human engineering. Right? So now we know that to build tall, you got to go deep with the foundation. Right? The Burj is no exception. That concrete slab foundation you see there, it's extremely solid. It's more than 12 foot thick, and it's huge. Right? And that might be enough in other places. But remember, Dubai is a desert, and sand is super soft. So in addition to that concrete slab, there are like 190 some what do they call hanging piles, that like basically long steel rods that drive into the ground more than 140 feet. So together with the slab, it can provide enough support for about 400,000 tons of a building. Right? And that might be enough in other places. But Dubai is both in the desert and by the sea. So at a depth of more than like 100 feet, salty seawater seeps into the ground, and it's going to corrode the metal piles. So not only do you need a massive amount of concrete and steel piles, there also needs to be a constant flow of electricity throughout the foundation to neutralize the ions from the seawater. And so it's only when you put all those three things together can you successfully put the Burj on top of that. And if you're not paying attention to the foundation enough, you might end up with the leaning tower of, if you said Pisa, you'd be wrong. I'm talking about the leaning tower of San Francisco, which you might recognize as the Millennium Tower on Market Street, just nearby. So this tower, right, opened in 2009, and it's been sinking and tilting since. People have poured like hundreds of millions of dollars in repairs. There's like huge drops in property value. Residents report like cracking sounds and window noises during high wind. And like apparently today, if you open your window at the wrong time of day, you get fined like $10,000 by the HOA or something like that. Right? So foundations are important. But we're not here to talk about architecture. We're here to talk about machine learning and AI. And the foundation for machine learning and AI is data. So, hello, my name is Cheng, CEO and co-founder of LanceDB. We're the database for multimodal AI. So from RAG to model training, LanceDB makes massive scale AI not just possible, but easy. I was one of the original contributors to the Pandas library, and I've been building data tools for almost 2 decades. My co-founder, Lei here, was a core contributor to Hadoop, which looks like some of you might have used, and led ML platform. I can't see who is who because there's like 2 giant spotlights shining into my eye. And he led ML platforms at Cruise for automation for years, right? So our team has contributors from Hadoop, Apache Arrow, Delta, many other important projects in the data ecosystem. So I think it's no exaggeration to say if you've kind of touched data in the past like decade or so, you've used projects that we made. So why does AI need new foundations? Well, first, it's the size. AI data is much bigger than tabular data, right? So if you look at TPCH, typical database table is around 145 bytes per row. If you add embeddings to that, it's immediately 25 times larger. If you're storing images, that can get up to 500 times. If you're storing videos, well, easily gigabytes per row, which is kind of crazy. In addition to that, right, the data is also coming in a lot faster than ever before. So instead of being limited by just manual human input to generate data, we're automatically generating data at thousands of tokens per second now. When you put these two facts together, the phenomenon that we see is that AI training data sets grow by several orders of magnitude every few years, right? So CFAR was roughly 163 megabytes, ImageNet up to about 150 gigabytes. Modern LLM training data sets, like text only, gets up to like 10 terabytes or ish, roughly. And if you're working with images and videos, foundation models for those, it's easily, you get to petabyte scale. So scale is one thing. AI workloads are also more diverse than what we had before, right? You're not just running analytics anymore. We're talking about training, oftentimes on multimodal data. And to support these runs, we need to work with the data for exploration, for curation, evaluation, and a bunch of other things, right? So if you just take a single training run, for example, first, you need to filter the data to get to the right subset. This requires a fast scan of the filtering dimensions. But remember, we're building on SAN, right? We need to shuffle this data so the model isn't seeing the same rows in the same order all the time, right? So now we need fast random access. And finally, here comes the seawater. We need to be able to quickly stream the data that you've identified in the right order to the right workers for distributed training, right? And most of the time from object store. Right, so you need to be able to work with large blobs effectively as well. So typically, if you look at existing systems today, they are only good for one, maybe two out of those three, but never all three. And I'm dubbing this the new CAP theorem of AI data. Right, this is a loose moniker because, as we'll show you, the real CAP theorem is unsolvable, but this new CAP theorem for AI data is actually solvable. So the consequence of building on top of these existing foundations is you often need to have multiple copies of the data for many different purposes, right? So when you have petabytes of training data, this is too expensive to have multiple copies. If you're managing those multiple copies, you need to manually translate between them, keep them in sync. You have to use different tools that are optimized for each task and each individual format. This makes it too complicated, right? And doing all of that means the most expensive hires in your organization are spending too much time managing low-level details on your data set rather than improving the model or improving your AI applications. So for larger organizations to work around these limitations, right, we've both seen these sort of Rube Goldberg data stacks, right, where each task come with its own copy of data in its own format and its own single-purpose compute. And then for different tasks, you have to go from system to system, translating and copying data back and forth. Right? So it becomes a nightmare to just navigate these systems. And when you try to build a data flywheel to support rapid iteration, that's all but impossible. Right? So we started LanceDB about 2.5 years ago by asking this question: what if we can have it all? And have your cake and eat it too. So let me introduce you to LanceDB, our new way of thinking about multimodal data infrastructure.
Thanks. So let's talk about how we make this possible. So we are rethinking the data infrastructure for those AI, especially those new generations of AI companies, as not your old father's data lake, right? So we want to design everything from the scratch on top of object store to be cloud native and try to get rid of all the baggage from the previous generation of data infrastructure. So the technical solution we choose is we develop an open source data infrastructure and the format on top of S3 or GCS on top of Apache Arrow and building Rust. We provide basically what machine learning engineer is most familiar with the SDKs in Python, TypeScript, or JavaScript. And it can actually store all the different modalities of data within this same infrastructure, so they can use the data frames, pandas, polars, or even SQL to just manipulate those data. And all of those data foundation is open source, so everyone can have access to it. It does not prevent you to use that into different cases where we still be able to deploy into very hyper large scale into enterprise and some like most demanding use cases in the world that actually store petabytes of data into LanceDB itself, and based on multiple layers of caching optimizations, we can deliver low latency and very high QPS much faster than many of the competitors in the market. And we have learned a lot of lessons from a previous generation of big data infrastructure. So we, from the very beginning, we designed this thing as a compute storage separation. So each of our customer will see different configuration and cost structure to make this system work for them. So the LanceDB open source is built on top of our in-house LanceDB Lance columnar format. We built that from scratch, try to address the 3 different workloads that we mentioned in the previous slides. By itself, it has 3 major components. First, it is a new file format. It's a new columnar file format that's designed with the support of fast scan and the support of O1 random access, which enable us to do a very fast filtering and shuffling just within the dataset itself. And we support storing large blobs inline so that user can actually use your existing pandas or DuckDB data tooling to directly operate on top of those data types itself. And by removing many of the storage assumptions from the previous generation of Parquet or like OCR, that we actually optimize the full access patterns for the new generations of storage device that we commonly see today, like NVMe or object store. And on top of that, we bring many AI native features that necessary for the table as a table format that we support multiple versions. Like basically, you can use these datasets as a Git repo that you can tag any tags with versions within this dataset to track your evaluation or experimentations within your activities. And a lot of our existing customers actually come to us for these zero-copy schema evolution features. If you think that you store petabytes of images or videos and you want to add embeddings or feature on top of it, you don't want to actually have like 2 different copies of that. We can easily to add single column with a very minimal computation and storage overhead. And other than that, thanks for our fundamental design principle try to get this random access working, we actually can build secondary index on top of this format to provide a very fast random access and search capabilities. Where in the very beginning, we use vector index as a proof concept to support to prove how fast the random access we can do. And by the end of the day, we can easily do millions of ops per second on our certain setup in our clusters. So the long-term visions we want to achieve is that we will within different workload, we will have single source of truth, but we can actually support from data generation, feature engineering to exploratory data analytics. And it actually can support training as well. And for LanceDB itself, all the other components will work well with the rest of open source communities to provide native and transparent access to them. And for LanceDB itself, we are more focusing on high throughput, high QPS serving directly from the object store of Lance dataset. So the word we want toward to is that we will have a single source of truth stored as a table within Lens, and we have different fast retrieval mechanisms on top of it. For example, assuming we have a table like this, we have metadata columns, we have prompt, we have like image or video columns, and also we have embeddings, right? Then within Lens itself, we have different index to accelerate access patterns on each of the different columns, where you can basically you can try to pattern match that into your different existing workloads like trainings, exploration based on, say, semantics of the data set, or you can use like OLAP to actually run the analytics of your stats, of the distributions of your training sample within your data set. That's where a few of our customers is actually found this can save them multiple copies of a petabytes data to just get one copy of that. So, and thanks for Anyscale, we have very deep integrations with Ray, and we have the same set of users at large scale. So why? I think we LanceDB and Ray have shared a lot of common design principles. First thing is like we want to be first level our class citizens of say be Python first APIs. So all our API, because the nature of our teams, we build on top of Arrow and Pandas, so it's very easy for user to adopt. And our open source offering is an embedded database where you can use that as simple as a SQLite. So that you can use that on a laptop, and also we have large-scale compute storage separations that you can actually run that as a large-scale system as well. And we want to be the data layer for AI practitioners to do data processing, model training, evaluation, and all of that. And Ray is the perfect match on top of LanceDB to be the computation layer to handle such workload. So since Ray 2.21, we have official Lens source in the Ray integrations, so you can directly use that today. It can directly read from any object store or local proxy-based file systems. And we are working on making the data sync into Ray as well, and we are actually actively working with the Anyscale team to make this happen. And other than that, many of our users is actually come to us for the large-scale schema evolutions, which basically are essential piece of feature engineering workflow. So we have that in Ray as well, and we are working on make sure this can be get into Ray release as well. So other than provide this SDK for our users, we use that in our production as well. We work with some of our customers to generate like more than 10 petabytes of image and video data set, and using that to be the base of feature engineering. And it runs on like more than hundreds of nodes and very large scale background compaction and the indexing jobs. We do have a LanceDB cloud offering as well, and raise a big piece of our backend indexing infrastructure to make sure we can distributedly to build large scale of index. Okay, thank you very much. And in summary, we are developer-friendly, open source vector multimodal AI database, and we have our GitHub repo here. Please check out, and we have Discord for anyone who want to join our community. Thanks. And any questions?
What's the latency between adding a new column and indexing? Like, what's the rough of the table, the calculation? Like, what have you seen from what kind of data to the point the index is? Is there Is there a mic? I'm going to repeat the question. So the question was, what's the latency between adding a column and indexing? So the data writing and indexing are separate activities that can be configured by the user. And it really depends on how you structure your process, how big is the data set, and what kind of index is being done. So anywhere from like a second to like hours.
So you mentioned compaction, which is pretty standard for like Parquet. So I guess when do we need to do compaction? Like what kind of scales of data does that start to kick in? Does it change the versioning guarantees at all? I guess like what would downtime look like for like terabyte or petabyte scale?
Right. So the question is like, what would be the occurrency of compaction and whether it will introduce downtime of live data. So firstly, Lance format itself is an immutable dataset, immutable data format. It has its own versioning, which means that the compaction will generate a new version of data, but old version is still accessible. The main purpose of is very similar to Parquet or Iceberg, that we want to run compaction because we have too many smaller files. We want to combine them together, right? That's where open source side you can basically trigger that manually by yourself. And our enterprise offering have a few heuristic measures to see how many smaller files within the same data set. And other than that, it's a background process that does not make a new commit as a new version. So old version is still there until like many days we have a clean up garbage collection to delete them. Did that answer your question?
Thank you.
Sure.
Just to follow on this question, let's assume that the data's in a GCS and 50 million rows, and it's like text data and an embedding that's about 1,024 dimensions. How long do you think that would take to query with like HNSW as the index type?
So question is 50 millions of 15 embeddings, 1,025. Yeah. And HNSW. So 50 million. Okay. So we have done some benchmark at around 50 to 100 millions with either IBIPQ or HNSW. HNSW we can reach to about 10 to 30 million, depending on your CPU type, on HNSW. And with the filters, with a pre-filter in, and we can, with like binary tree Scala index, we can get around 40 to 50 combined hybrid search combined search together with 50 milliseconds.
Thank you.
Yeah, from GCS directly. Yeah. From GCS directly.
Yeah, Leo's manually running through the SIMD code here.
So sorry, just like a rough rule of thumb as I think about this stuff. You guys are like, could be 10, 100 times faster than Parquet for reading an individual record, right?
Right.
What is the overhead cost relative to Parquet of like scanning an entire file? I don't want to do any filtering, no pruning whatsoever. I just want to like scan the entire thing.
As fast as, okay, actually, let me repeat your question. So if we just do pure scan compared to Parquet, where we are in terms of benchmark, there are two aspects of this. One thing is that how aggressive Parquet is compressed. Okay, so that's one thing. For us, we use those like O1 based encodings. At most, we can compress to up to two times of that. But if the size of Parquet and us is the same, similar, there are another two aspects of this. For the best Parquet libraries, we are as fast as them. But many of the libraries out there are not that fast, so we are actually faster than that. Yeah.
So it depends on the Parquet library.
Yeah, Parquet libraries, especially.
Yeah.
There's essentially no
Yeah,
overhead in general.
Yeah. in general, we can basically eat through all the bandwidth of a VM on Google or AWS. Yeah.
Yeah, if you are looking for a fast Parquet reader, talk to that guy over there.
Yeah.
Yeah. Hey, what's up, Jay? How you doing, man?
Yeah, is your database good at searching, querying by structured data like SQL?
Yes. So questions is our table or database good at searching or serving of SQL-ish data? Yes. As a serving mechanism, we ask in terms of some latency, we can ask even faster than Redis when you configure that correctly. The only thing that I think we trade off is like our Redis throughput is not as good as a Postgres. Yeah, but it really is very good.
Yeah, and you mentioned that your database can handle with very advanced RAG queries.
Yep.
Yeah, can you elaborate? With the samples, what kind of examples of advanced RAG?
Yeah, so typically, these are things that are like, I need to have multiple modes of retrieval, or if you're talking about multimodal data, in practice what we find is that many of our users get better results having different embeddings from different models for different pairs of modalities. And so the sort of top level retrieval they're looking for is, okay, I may have multiple embedding columns, or I have like an embedding column and a full text index built on the text data. How do I search both of them, combine them, and then maybe plug it into a re-ranker for like really like production quality retrieval, and then layer on these SQL style filters on top of that are like, maybe it's like a list of tags intersection, categorical, like I want top 10 matches only from these document sources that only apply to these customer IDs, and so on and so forth. Yeah. Does that answer your question? Okay, cool.
I had a question about, y'all are multimodal, but is this, number one, still good for stuff that's, like Parquet style, numbers, floats, decimals, strings? And then how does that perform over, say, text? And how does text perform over images? How does images perform over video?
Right.
What are like the various trade-offs, and what do you see where that stands? And there's like a spectrum of multimodality?
Totally. So the question for the other side of the room is, what about performance for different modalities of data, from like images, videos, to text, to just pure tabular data? And so I think this is a great question because it hits on one of the key trade-offs with Lance format is, in order to have good scan performance and good random access, you can't use file level compression. So we're trying to solve that for different data types using encoding. So for images and videos, typically they are compressed at the record level already in their binary representations. It's almost 5 o'clock. So it's not, there's no difference there, right? So for strings, yes, that makes a big difference. So we've added FSST, which is also used in DuckDB, and that's basically compressive string encoding that also preserves random accessibility. So that gets us pretty close, like almost the same as Parquet on disk size for strings. And then we're working on various encodings like bitpacking and others from like Fastlanes for, let's say, integer compression. And then we'll work on floats. And then there are some partners that we're working with that are looking to add like time series encodings and maybe like rolling window functionality and things like that. So if you're interested in any of those, definitely talk to us. So we've made the encoding subsystem extensible. So in Parquet, if you want to add a new encoding, you literally have to touch everything. Whereas with Lance, think of it more like MP4, where you can, or like, it's like container format where you can download different codecs. So you only have to write the encoder and decoder to add a new data type there.
If I have a streaming data in, how do I say update my row somehow?
Right. So our update is including writes, is relatively expensive. So basically, we will overwrite that piece of fragment within the whole data set and mark that as a new version of this data set. So next time you access, you can find that.
So there will be new files created?
Yeah, new files. We don't do in-place updates. But yeah, so we are running out of time, but
Let's
let's talk.
take one last question, and then we can talk offline. Yeah.
Yeah.
So for managing embeddings, it'd be best practice to be able to define your schema for your content. Right? From what I can tell, one of the value adds of LanceDB is embedding APIs that you don't have to go and try to define like the schema for your embeddings. You just kind of attach it to the content schema that you're doing. Is that an accurate description?
Yeah, so you're talking about sort of the API for the LanceDB SDK. So yeah, there's an embedding function, embedding registry functionality where you can declare, when you declare the schema using pedantic, let's say, you can say this vector field is generated from this embedding function. So then when you insert data, you only have to insert the raw text data or like the raw image data. And then the metadata that you declared the schema with will trigger LanceDB in the background to automatically generate the embeddings for you.
Okay, and that's just dependent as like the embeddings column.
Yeah.
Right, exactly. Yep. Okay, cool. Thank you so much for coming to the talk so late. We'll be hanging around for a little bit.